My talk is addressed to pessimistic Python programmers who haven't done a lot of property-based testing. So if you're one of those people who doesn't fervently believe in testing, this is probably not a good talk for you. I'm one of those people who believes that all my code is buggy, and so things, well, I'm pessimistic, and so that's why this is great for me. If you don't know Python, this talk isn't so good for you because Hypothesis, the library I'm talking about, is a Python library for Python code, and all my examples and so forth are going to be in Python. So if you already know about Quick Check, the original Haskell Quick Check, if you've been doing properties-based testing already for a while and know all about it, then honestly, you might want to just stop listening to me, install Hypothesis, and get started. My recollection is that it took me like 3 minutes to find a bug in my code. I think it was probably more like 3 hours because I'm one of those people who actually read some of the documentation first, but it was really, really easy and straightforward. If you already know the concepts and you're familiar with Python, you might just want to start using Hypothesis and see what you get out of it. Okay, what you should expect to see are extremely simple code examples. And the reason for that is partly because if I showed you a clever bug, everybody would try to figure out what it was, or at least that's what I always do when that comes up, and lose track of what I was trying to say. So the code examples are so extremely simple that they shouldn't distract you at all. And I'll mention that on the Hypothesis site, there are some tricky code examples that you can enjoy reading and seeing how Hypothesis finds the bugs in them. Another thing is that I'm going to talk a little bit about my own personal experience, not because my life is inherently interesting, but because I think that a part of the personal experience I had is something that other people who have used Quick Check have also had. And then also in this very simple and rather short talk, there's going to be pointers to other sources on the Hypothesis website and elsewhere, because there's just a lot of really good, clear, helpful information out there besides what I'm giving now, so I might as well just direct you to it. Okay, so to start with, I'm going to talk about unit testing, and that's, of course, what Hypothesis isn't. So the idea is that I'm testing a convert from nat function. All it does is it takes a Python integer and a base and gives you the list of digits in that base that are corresponding. And so supposing I've written this function, then I want to test it, and I want to perhaps unit test it because that's all I have, or all I know I have. And so I'm using PyTest for whatever reason. And so I write a few simple unit tests to try to catch likely modes of failure for this really simple function. And so I could do a lot of things. You can see me checking that it works on 0. The way I've defined this function is that 0 is no digits at all, because otherwise I'd have to wonder how many digits. So I went with none. And then you have to check on different bases. It should work with all of them. And then you have to check for large values with small bases and small bases with large values, and you should check exceptions as well, and so on and so on. And while it's good to do this, it's obvious from looking at this that it gets tedious. Okay, but don't get me wrong. I think unit tests are, in fact, a good idea. They do some stuff that you want to happen, and there are libraries in Python that support it rather well. There's the unit test library that is right in Python, and there's PyTest, which is a bit more of an adventurous sort of library that is less sort of classic and uses some more reflection and so forth. But they both have their good points, and it's really good support, really. So why do you want unit tests? Well, they partially and implicitly specify the code that they test. So they give some idea, if the programmer wrote them, of what they think their code ought to do. They catch bugs, and when you do some changes, they catch surprises that you didn't expect. So unit tests are good. But now hypothesis testing can be better. And so here I'm going to talk about how I go about writing a hypothesis test. First, I have to actually come up with a statement about what my function should do. And what you see there is the theorem that I have up there, which is actually a mathematical theorem. It says for every integer, which happens to be at least 0, that means all the natural numbers, for every base that happens to be at least 2, and base 1 is degenerate, so I avoid it, and the others are meaningless, then I say if I convert from a nat to that base, and then I convert back to the natural number from the result, then I'll get the value I had originally. So that's what I'm saying. And this is one of the really standard ideas, one of the most basic ways that you'd come up, that you'd do testing. And as it happened in my package, in this little library that I had written, I had both of these functions already available. So this was a really dead simple and obvious test. So what I have on top is the thing I want to test. And what I have on the bottom as the test is really the same thing stated using a Python function and a hypothesis function, really a decorator here. And as you can see, the translation is almost exact. So I have two things that are given. One is that value, which is greater than, which is at least 0 as before, and one is that base, which is at least 2 as before, and both of them are integers. So that's all in the arguments to the hypothesis given generator. And then my function just takes those both as arguments and tests that the fact I'm interested in is true. And so that function is just a statement of the second half of the theorem. Okay, and that should, I think, look pretty straightforward. The two things match. And here's another example where I did something slightly different. I decided that for my function, there should be no leading zeros in the result. And here I go ahead and I check that fact. Here I don't have to rely on another function that happens to be in my library. I just go ahead and I check the result. Okay, so what does hypothesis do with the small amount of code that I've written? It comes up with arguments corresponding to value and base. So it generates that arguments based on its strategies. It runs tests. It runs the tests that I've written for every one of these pairs of arguments. Whoops. And then it stops at the first failure, if any. If all the tests succeeds, then it just reports that. But if there's a failure, it stops at that failure and it reports what particular values caused the failure. And it also stores all that work that it did in some kind of a database, remembering what the result of the test was. And this is really a very high level description of what is going on. Underneath the hood, hypothesis has fluctuated a lot, but it's able to do all these things, to synthesize your arguments, to run your tests, to remember what happened, to report the failures, and to tell you what it failed on. Okay, and at this point, I'll say that property-based testing is great. It is so much more powerful than unit testing, generally speaking. For one thing, it's an explicit specification of what the code does. So the unit tests were implicit. You could look at an example and say, oh, that must mean that some property must be true of this function. But in hypothesis, you're explicitly stating something that must be true of the function. So it's much more useful, clear, and readable documentation of the code to anyone who takes a look. You can also get more tests actually executed, more valuable tests actually executed, while writing less testing code. And that's obviously a good thing. One of the ways in which it's particularly obvious is if you're one of those people who test pretty soon after you've written the code, or even before, you write the test, you write the code, and then you realize you need an API change. So you need to switch around functions, change something somehow. If you've written unit tests with comparable coverage, then you probably have to go by hand and fix up 51 so they take the arguments in the new way. And that's a huge pain. If you've written a hypothesis test, maybe you just have to fix up 1 or 2 lines. That's really great. So also, you use somebody else's code, the hypothesis code, the strategies code, to choose your examples. And that's actually surprisingly good. You might think that that's not so good because actually, after all, you're wanting to think of examples that might break your code. But it turns out that often you know less about the possible examples that are available that have that type than, for example, the hypothesis strategy does. And I found that out in sort of the hard way when I was working on a library when I hadn't, for some reason, realized that decimal has non-numeric values essentially in it. So there's a decimal class in Python, and it's kind of like the float class in that it has not a number and infinity, I think. And of course, that hadn't entered my mind until my code started failing lots of tests, because hypothesis' decimal strategy, of course, thinks of those and starts flinging them at the tests immediately. So that was really good. It makes you realize, hey, something that you just hadn't thought of at all. So also what hypothesis will do is, yeah, it generates a lot of tests, but it remembers the one that failed. And the next time you run your test, it goes for that one. It doesn't try all the ones that it had tried previously before it found the failure. It goes right for the one that failed. And that's really nice because if you're debugging, you can just run that one test, blammo, it'll hit the one thing that failed last time, and you can step right into the debugger if you want, or anything else that is useful to you, but it goes right to the failure, and that's great. And you configure hypothesis a lot. I don't always mess with all the configurations, but if you really think that 5 tests are quite enough, if it passed 5 tests, then you're happy, then you can tell it to stop at 5. The default is more like 200 or something. But if you prefer 5, 5 is good, and so forth. It's very configurable in a lot of useful ways. Okay, but it is not all fun. So it's not easy, because in many ways you have to think harder to use it. So sometimes it's hard to come up with a good specification of your code. And the really pedagogically minded would say, well, if you can't come up with a good specification of your code, then that's a sure sign that you don't know what it's doing and so forth. But sometimes that isn't really true. It's just hard to say what it really is doing, either for various reasons or because it's hard to figure out in Python. So it can be hard. And actually unit tests, using unit tests, that problem just goes away because you can cheat. You can just write a unit test with some arguments, find out what the value of the function is, and just plug the function into the result, and then you're done. You don't have to do any thinking with a unit test if you don't want to, and then when you notice it changes, then you might have to think a bit about what was going on. But you can cheat with unit tests, and you can't really cheat with hypothesis tests. So it may also be that whatever you really want to test will take a long time to test, but that would probably be the case with unit tests as well. And it may be that the values you want to test on are ones that hypothesis doesn't already have a strategy for. Now, it turns out that actually hypothesis has higher level strategies that allow you to build your own strategies from its simpler strategies, and also that it has an extras library so that people can contribute strategies that need to be built from scratch or independently. And to this date, I have never had a problem with not having a way of generating examples for my tests. So all that work that you might have to do, you get a lot in return. That's the great thing. Okay, so now this is where I get to the personal side. So back in the day, I used to believe that property-based testing was great, but it was only good for functional applications. And this is because I first saw it in Haskell, thought it was great in that. Haskell is the purely functional programming language. And the examples that you typically saw at Quick Check were mathematically oriented or things that Haskell could do simply, probably not even with monads. And so it seemed like it was really functional. It was about testing functional things. So that's what I believed until I ended up taking over PyUdev, which is a library that wraps libudev. And libudev is a library that accesses the UDEV database and sysfs attributes and lots of things. Well, not lots and lots, but numerous things having to do with devices. So it's not a highly mathematical, highly functional sort of thing. It deals with real databases and real directories on a real system somewhere. What I found out was that the original developer had already written lots of property-based testing. He cobbled them together using PyTest very cleverly in a lot of ways. So he used a lot of ways to do the property testing properly. He actually ran UDEV admin info, parsed the output of this, and used that as an oracle for his PyUdev tests. He also made mock objects when he thought he needed them. And he'd make sure that the PyUdev functions were self-consistent. Those were kind of his main things. He had lots of tricks. And I thought it would be good to hypothesize it because of really a couple significant problems. Even though this was really great and it was well done and really opened my eyes to the possibilities of property-based testing, there were some issues, and I went ahead and hypothesized it. So here's a simple test using hypothesis. And what we're doing here is checking that if you have a device and you use its so-called sysname, if you have that device and you use the sysname to get a device, a new device from that same subsystem and sysname, they'll actually be the same device. A very simple test of self-consistency to exercise this. And it's kind of a boring test, and that's why I only do 5 examples of it. And here the arguments we give are the context, which is PyUdev's context. It's essentially the mess that it uses around wrapping libudev. And, also what I do is I just have a static list of devices, and I make a strategy by randomly sampling from that list of device objects. Okay, and so why was it worthwhile hypothesizing the test? Well, because what the former developer had done in PyTest wasn't as good. So if he skipped an example, he reported it. And that wasn't so great because I was getting hundreds of skipped tests when some large fraction of them were just all trying to test the same thing. And with hypothesis, I could change that around. I get a skip message, not per example, but per property that I'm trying to test. And that's a whole lot more valuable. So there was a lot of benefits from this. I understood what I was skipping. Everything was simpler. And the benefit was that bugs started falling out. That might be sort of a disbenefit, but also a benefit. I found bugs in PyUdev. I found problems in libudev. And I found problems in the structure, actually, of the UDEV database. It wasn't matching reality. So all that just because I at a bunch of hypothesis tests. And by the way, I am still finding bugs in PyUdev and problems in LibUdev up until a couple of weeks ago, and I hypothesized the tests in PyUdev a year ago, I think. So actually some new bugs, I think, are popping up in LibUdev, and we're eradicating a few more bugs in PyUdev. Okay, so I think property-based testing is great, and I think hypothesis is great. So hypothesis, like I said in the beginning, as far as I can remember in the hazy glow, it took like 3 minutes. It was so easy to get started and so easy to find bugs. And I already knew that property-based testing was great. The whole idea is really, really powerful and really, really helpful. So reasons that I've mentioned is that you remember the examples that failed last time without having to write them into your test code. You have an explicit statement about what your function or method should do, and you're using somebody else's code to generate examples. And often that is better than you could do yourself. And there's other things that you would discover if you kept on working with hypothesis. Okay, so I'm going to admit that there is, all is not perfect. Okay, so hypothesis is a testing library which works with multiple testing frameworks. It has to work with unit test and PyTest. And so it has to communicate with them. And as far as I can understand, they really only understand success and failure. So I have a problem with that because when I'm testing PyUdev, I actually synthesize my device examples out of the real world, the machine I'm actually running on. And I can't know if I'm going to have lots of good examples or 0 good examples. So I would like hypothesis and PyTest, or hypothesis and unit test, to be a little more flexible, so that if I really tried all the examples I wanted to and everything was good, all of them passed, then I could record success. If I tried examples and I found a counterexample, I could record failure. But if I just couldn't find the required number of examples, then I would say I skip this test. That's the rational thing to be able to do, but it turns out to be kind of hard. So this is a simple test using hypothesis that has been rendered not so simple because I have to worry about whether I have enough devices that have the parent and the same subsystem on this system. So I have to statically calculate the list. Then I have to use PyTest to skip it if the list is 0. Then I have to pass that strategy, pass that list of devices to my sampled from strategy, and then I can run the test. So if I don't have that sequence there, then what happens is that the test is going to fail when I'd rather it was just marked as skipped. And I would like to have something simpler where I could just say, grab me the relevant devices, and then it would be handled properly and skipped properly. Okay, so that's the fly in my ointment at this time, the admission that hypothesis doesn't solve every one of your problems perfectly. Okay, and so this has been a very short talk. Yeah, so it's been a very short talk, and that's in order to finish up quickly, but I don't want to give you the impression that I've actually discussed everything there is to discuss about hypothesis or really about property-based testing. So I'm going to tell you a smattering of things that I haven't discussed. The hypothesis developer is working on a version in Java. Since I don't use Java very much, I've only just glanced at it. The idea of property-based testing has caught on, And apparently even the library, the C property-based test library is pretty good, even though you would think that might be very difficult. So according to the hypothesis developer, the one for C is pretty nice. Hypothesis does something fancy. So if it finds an example that contradicts your hypothesis, if it finds a counterexample, it'll try to make that example smaller and more comprehensible. Now, generally speaking, that's not an issue for me because you can't make a device. If the device is the counterexample, you can't make a device smaller. And so most of my examples don't really need to be minimized. So I admit I don't know very much about that, but I have seen it a bit in action in Hypothesis's own self-testing. There's a useful function called note that allows you to display additional information only if the test fails. So you don't display it if it succeeds, but if the test does fail, then that information will be part of Hypothesis's output. And to be honest, I don't use that much when I'm working on my own system, but for continuous integration where you can't interact directly with the tests, I find that to be really nice. So it'll give you that little bit more of information that can help you figure out why that test is failing. Hypothesis has a bunch of higher order strategies from which you can build strategies, and I use them a lot to build, for example, devices, strategies, and so forth. They're very nice and very convenient if you're used to the notion of higher order functions and so on. I haven't discussed how to write your own strategy from scratch because I've never been put in the situation where that struck me as really necessary or useful. I'd like to do it sometime, but I would have to have some justification as that it would actually gain me something, and Hypothesis' other facilities have made it unnecessary. There's lots of ways, as I said, in which you can configure Hypothesis globally. It also has configuration profiles, so you can have different profiles depending on whether you're running on your own machine or doing continuous integration, and you can automatically load those and go ahead with that. That's admittedly somewhat new, and I haven't done much with that. You can actually just use Hypothesis not as a testing facility. And so this is kind of interesting. If you're just curious about finding an example of something and you think there's no such thing, you can ask Hypothesis, and Hypothesis can find it. There's some nice examples on the Hypothesis website because the developer is interested in voting systems, and he uses Hypothesis to show how different voting algorithms can yield different winners for the same votes by a population, kind of thing. So you can actually use Hypothesis just to explore and find things out that you might not have known. Testing GUIs, I have no idea how you would do that, but it's, I think ingenuity would yield you great rewards there, but I don't really develop GUIs. So there's the coverage tool that a lot of people use for Python, and that can be more, between that and Hypothesis, you can get more than just a measure of quality. It's very interesting sometimes when you make a change to your code and you have a function that had 100% coverage beforehand, and now even with all those Hypothesis tests, it doesn't have that coverage anymore. And that's an interesting hint to you about something surprising about your code, and it acts actually as debugging help. So more than just a single number measure of quality, it helps you zero in on things that are wrong with your code. It would also obviously be possible to use strategies to generate mock objects. And so everybody will know about the notion of mock objects, fake objects that you can run your code on and check that various things have happened. You could do that using Hypothesis, but again, I haven't had to attempt that, so I haven't done so. And also, Hypothesis will allow you to take an entire class and run automatically tests on all the methods in the class. So if you have defined a class where the methods interact on internal objects, you can actually use Hypothesis to run, without your specifying in what order, numerous tests calling multiple methods of this class, which will check whether the properties you care about hold. And yeah, technical things, PyTest and unit test, supports many versions, supports both CPython and PyPy, and tests itself with 100% code coverage on itself. Okay, so this Hypothesis, as I said, is great. The developer is going to get out of developing it. He has announced this. He doesn't really make any generally regular money on this. It's a hugely valuable library, and I know that a variety of people use it. This is the kind of open source thing where it would be great if it could be kept alive and kept going and kept supporting. And at this point, I'm sort of wondering, is there some way that open source can be showed to work by keeping this thing going? Because it is so good and so valuable to so much open source code. Okay, and that's it.